Alright, so today we're going to go over question 1 of the 2019 Sir Isaac Newton Physics Contest. This question asks for the minimum number of blocks needed, such that if you stack them one on top of another, the top block can completely overhang the bottom block. This may seem very confusing at first, so what we're going to do is collapse the problem to simpler, smaller ones. We're going to define a variable n to be the number of blocks. And we can try for small values of n, what is the maximum overhang possible? If we have n equals 1, the result is a bit trivial. It's just a simple block. And since there's only one block, the maximum overhang is 0. If we get n equals 2, it's still pretty trivial, but it's a bit more interesting. We have the first block here, and natural intuition tells us that the second block should be here, with the dotted lines. But why? Why is the second block there such that half of the block overhangs it and half of the block doesn't? Well, this is actually because the center of mass of the top block lies right above the edge of the bottom block, and that is what we wish to create. We wish that no matter how many blocks are on top, the center of mass of all those blocks is before this edge. So the center of mass has to be from there all the way to there. But in order to maximize the overhang, we want the center of mass to be exactly at the edge. So what's the maximum overhang for this? Well, we know that the length is 20 centimeters, so half of the length will just be 10 centimeters. So the maximum overhang is 10. Now, n equals 3 becomes much more interesting. We have a solitary block at the bottom, like always, but this time we can add 2 blocks on top, such that they're stable by itself, and that the center of mass of the combined 2 blocks is exactly at the edge of the first block. Now, this sounds like a very familiar problem to what we've done before. Look at the n equals 2 case. We wanted to create a stable configuration of 2 blocks such that the overhang is at a maximum. This can also be thought of as a stable configuration of 2 blocks where the center of mass of the 2 blocks is at a maximum. Now, we can use the center of mass equation, or we can just use common sense or symmetry on where the center of mass of the n equals 2 system should be, which we know is here. But to help us with future problems and future cases, let's just define the center of mass formula. So the center of mass is equal to the location of the first center of mass times the mass of that object plus the location of the second center of mass and the mass of that object divided by all the different masses, or the total mass. So for the center of mass of the n equals 2 case, we have, what's x1, the center of mass of the first object? Well, that's just going to be x equals 10, because the total length is 20 and half of that length is 10. And let's just call, for simplicity's sake, that the mass is 1. It will cancel out at the end, so it doesn't really matter what we choose the mass to be. The second block has a center of mass which is exactly at 20, because that's what's defined. The center of mass of the second block has to be at the edge of the first block, which is 20 away from the origin, which we can call the origin like here. And the mass of that, since they're all identical blocks, it's also 1. And the total mass would be 2, and that gives us 30 divided by 2 equals 15. So we know that distance is 15. Or we can say that distance is 20 minus 5. And we'll see why this is very useful in the future. So we can actually copy and paste these two blocks that we already created and move it down here. Over there should be fine. Such that if this is 20 minus 5, and that's 20, the second block is 20, then this distance must be equal to 5. So we already calculated that the maximum overhang here is 10, and then we added to the maximum overhang here, which is 5, so the maximum overhang for n equals 3 is 15. I'm just going to redraw the n equals 2 case, just for future reference. Now we can go to n equals 4. You might see the pattern already, but if you don't, it's alright. We have the bottom block, and we wish to have a configuration of 3 blocks such that it's stable and the combined center of mass is as far away as possible, which we've already come up with for n equals 3. We have the maximum overhang, which is equivalent to having the center of mass as far away as possible. And it's a bit hard to use symmetry to determine the center of mass, so we can use our formula. The center of mass of when there's 3 blocks of this entire a system of 3 blocks, is we have our first block, which has a center of mass located 10 away, and the mass is 1. But to make it simpler, we can just treat these two objects as just one single mass. That's a mass of 2. So we know that the mass here is 2, but what's the center of mass? Location of the center of mass. Well, we've already defined that to be exactly 20, because we needed to take these two blocks and place them such that their center of mass lies directly on top of the edge of the bottom block, which is located 20 away. And the total mass is 1 plus 2 equals 3, or 50 divided by 3. And we can write this as 20 minus 3.33. So again, we can just take the previous configuration that we already had, make a copy of that. Oops. I don't know what's wrong, but you know what I mean. We can make a copy of that such that we have a total of 4 blocks. We already know that the center of mass needs to lie over here, and that distance is 20 minus 3.3, repeating as we calculated. But since the second block has a length of 20, the overhang of the second block with respect to the first block is equal to 3.33, repeating. We know the overhang here, as we calculated before, is 5. We know the overhang here from the fourth block to the third block is 10. So the total overhang is 18.33, repeating. Or we can write it as 10 plus 5 plus 3.33, repeating. You might see how we can repeat this for n equals 5. and then n equals 6, and n equals 7. But if you're keen enough, you might spot a pattern such that we don't have to go through that mess again. We can rewrite 10 plus 5 plus 3.33 repeating to be 10 plus 10 over 2 plus 10 over 3. So that's for the n equals 3 case. And you can guess, and you'll be right, that for the n, that's for the n equals 4 case. And you can guess, and you'll be right, that for the n equals 5 case, the maximum overhang would be 10 plus 10 over 2 plus 10 over 3 plus 10 over 4. So what would this be equal to? Well, we know that the first three terms is equal to 18.33 repeating, and the next term is equal to 2.5. So if we do the math, we have 20.83. So the maximum overhang, if you have 5 blocks, would be 20.83. And since 20.83 is greater than the length of a single block, then the top block will completely overhang over the first block. So there we have it. 5 blocks. We need 1, 2, 3, 4, 5 blocks so that the top block completely overhangs over the first block. And there you have it.